Now, let us look at how do we do the analysis for a flanged section. Okay. So, flange sections are quite common in constructions, as you all know. A precast or cast in place flange section which will have flanges either at the top or bottom or at both top and bottom, right. So, you have this kind of a situation. Now, depending upon the geometry of your T section or L section, you can have two conditions and ultimate. So, the first condition is the neutral axis can go higher than that of the thickness of the flange, it can get into the web, and the XU can be greater than the depth of the flange. But because the flange width is large, typically this is more common, right. This is more common, but we cannot say all the time. It also depends upon your width of the flange and your area of the pre-stressing steel, right. So, you will have XU will be there, because if you have low reinforcement ratios, this is quite common, we will have when you have low reinforcement ratio, right. If you put a lot of reinforcement, then your neutral axis can be dragged below the flange into the web region. So, the effective width or breadth of the flange is determined from the span of the beam, breadth of the web and depth of the flange and so on. These provisions are given in 23.12 of IS 456, that tells you what should be the width of the slab. You should consider that as part of the flange, right. So, all these provisions are already given, we have already talked in advanced reinforced concrete class. So, you can refer the code provisions or the lecture materials of NPTEL course on advanced reinforced concrete design. Now, when XU becomes more than the depth of the flange, ideally then only this becomes like a flange section analysis. When XU becomes less than the depth of the flange, then ideally actually you are doing a rectangular section only, but only thing is the width of the section will be BF. And when the DF, when it is less than 3/7 of your XU, then this ensure that the compressive stress is constant at 0.447 across the entire depth of the flange, right. So, what does that mean? So, if your depth of the flange, when this condition you can see here, when the DF it is less than, when DF is less than 3/7 of XU, right. So, we have seen that this distance, this constant parabolic region, right, that goes on for a strain distribution for a distance of 0.0035 to 0.002. So, if you go back to your stress strain curve, you see that FC epsilon c, you get this in that straight, right. So, this strain is after 0.002 until 0.0035, this pretty much remains flat, right. Okay. So, for strain higher than 0.002, the stress is going to be 0.447 FCK. So, that is what we are saying. When the depth of the flange is less than 3/7 of your XU, then you will find that the entire flange will be subjected to constant stress of 0.447 FCK. So, this can be clearly shown here, because this, if you look at the XU, so if I divide this into, this is going to be 4/7 of XU and this is going to be 3/7 of XU. That is what we are saying. When DF is less than 3/7 of XU, this stress will be constant at 0.447 XU, right. So, for a flange section analysis, the strain distribution still remains same. Now, I can, depending upon the contribution of web and flange, I can decouple these internal forces into two things. I can take like this, what we have seen, the entire web is as one rectangular section, right, and then I can take this 2 overhang flange as a one section into a combined one section. So, this is 1 and this is 2. So, that is what we are doing here. So, this is for the first segment. I say that the CUW is going to be the compression force that is coming from web. Now, I can quickly calculate what is CUW, right. So, CUW is going to be 0.36 FCK. Here it is going to be, instead of B, I am going to have BW times XU, right. And if I know for any assumed value of XU, once I get my CUW, then I can find out from the strain how much is the area of pre-stressing steel that is actually balancing only the force in the web. So, this TUW now can be written as APW times FPU, right, a portion. So, AP can be divided into two things, APW plus APF. Now, APW is the amount of steel that is required to force the compression force from the web region only. Now, CUF can also be now done. So, what is TUF here? That means whatever the remaining. So, it is going to be APF times FPU. Now, what is CUF in this case? If CUF is, if you are finding DF is less than 3/7 of your XU, CUF will become again 0.36. Okay. Now, you see here the entire region is in constant. So, it is not really 0.447. So, it is going to be 0.447 FCK BF times DF. This is going to be the compression force offered by the flange, because the entire flange is having constant stress of 0.447 FCK, right. So, that is what here we have written here in terms of internal forces. Now, this is the portion, okay, so this is one thing. So, I have to subtract BF minus BW. So, if you go back, in this case, I should not take the entire BF, I should take BF minus BW times XU. So, that is what we have shown here, and rest of the things are all same, okay. So, this is valid only when your DF is less than 3/7 of your XU. Now, if the depth of the flange is higher than 3/7 of XU, now you will find that it's the stress block in the flange is not constant. You also have some parabolic portion, it is there, okay. So, definition, APF is the part of AP that balances compression in the outstanding flanges. APW is a part of AP that balances compression in the web. FCK is a characteristic compressive strength of concrete, and FPK is a characteristic tensile strength of pre-stressing steel. And TU is equal to CU. So, again we have to always equilibrium condition has to be satisfied. So, the TU will have two components from web and flange. Similarly, compression force will have two components from web and flange. So, we have to ensure that. And this is the overall equilibrium. When I put all of them together, so this is your equilibrium condition. So, now we have to ensure for a particular value of XU, we satisfy this. If we do not satisfy, then again you go back and use, either you increase or decrease XU, and then repeat the process until equilibrium is satisfied. Once equilibrium is satisfied, you can calculate your internal forces like this, and you can find your moment resistance. Now, how do we get the moment resistance, right? So, now let us say that I am taking moment resistance from, for each system, let us say that I am taking moment resistances, right. So, for this I am taking moment resistance about, let us say, at this location 0.42 XU, then it is going to be, because these two are in equilibrium, so it is going to be TU minus times D minus 0.42 XU, which is your lever arm. For the second one, the lever arm is this, which is nothing but d minus 0.5 df. Okay, that's what we have. So these are the forces. So, and this moment resistance will always be additive, and when you do that, you get your moment resistance. Now, what is the again the curvature is very simple, epsilon cu divided by xu. So that always remains. Curvature is nothing but the rotation of the section, so that we can get it. Now, again strain compatibility approach, first we can assume xu of the, how do we go about it? You have to assume xu. So first you can assume as a first trial, right, xu equal to df. So calculations are similar because now the neutral axis is equal to df. The calculations are similar to rectangular section with b is equal to bf. If tu works out to be greater than cu, then you increase xu. So the moment xu becomes more than the depth of the flange, then this actually becomes a flange section. Now again, conditions may arise when the depth of the flange is less than 3/7 of xu, then the calculation is simplified like what we have seen previously. Once xu again is assumed, then we can get your epsilon pu again from similar triangle using strain compatibility. Okay, and FPU is calculated from epsilon pu, and I can get my APF and APW and calculate your compression force from web, compression force from flange, tension force from web and tension force from flange. And now we add all of them, tension should be equal to compression. If this is not satisfied, again we are going to iterate it with a new value of neutral axis depth till the convergence is happening. Then you get your moment resistance. Once you satisfy, like what we have seen in the previous slide, you can calculate your moment resistance and then even curvature at ultimate. Okay. The same way we can use approximate method for doing the flange section analysis also, right. In strain compatibility method, again the difficult step was to estimate the xu because we are doing it in an iterative way, right. So IS 1343, it allows to calculate these variables from table 11, again like what we discussed for a rectangular section, same is applicable for flange section as well. Now here the pre-stressing steel in the reinforcement index is given as APW times FPK by BWD into FCK. Now the capacity now can be compared with the demand under ultimate loads. Now let us see how do we calculate this. Same way, only this the notations are different. It is the amount of steel that is there in the web. Okay, so in the approximate method, the first step, instead of going in terms of xu, directly we are going to say that FPU is equal to the yield stress, which is 0.87 FPK. So this is an assumption that we are doing. We are assuming that. Then once this is assumed, I can calculate what is the area of pre-stressing steel that is helpful in satisfying the equilibrium for compression force from outstanding flanges, because again I have told you this T section what we are actually doing is we are converting this into two things, right. This entire thing will be taken as one section. Okay, this is one and this is taken as another thing. Okay. These are outstanding flanges, only this. So the AP also, that is the reason we said you will have APW plus APF, right. So let us say you have some steel AP. So this is how much is the area of steel that is helpful in satisfying the compression force from the web and how much it is effective for satisfying the equilibrium for compression force from the flange. So we can calculate this APF and APW from the respective equations. Then you can get your reinforcing index based on only APW. Then you get your FPU from table 11. Once you know the reinforcing index, I can go ahead and calculate my stresses. Now, what we are doing is we get your FPU and you go ahead and compare whatever that you have assumed. So, the first iteration we have assumed this 0.87 FPQ, right. In a way what we are doing is instead of assuming XU, we are assuming FPU, which is an indirect way of taking different values of your neutral axis depth, that is all. So, we have to repeat these steps 1 to 4 until the stress that you are getting from the table is close to the previous assumed value. Once you do that, basically you have come up with a equilibrium condition. So, then you can go ahead and calculate the moment resistance. Now, again one more condition can happen. Now, when the depth of the flange becomes more than 3/7 of your neutral axis depth, now flange depth is larger than the depth of the constant compressive stress. That means, here when I put the stress block, let us say I put here. So, what we are saying here is, let us say this goes like this and then comes back like this. So, that means this depth what we are taking, right, this is up to here, right, this is 0.447 FCK. So, that means this depth df as, or in other words, this is basically your 3/7 of your XU, or in other words, df has become less than 3/7 of your XU. So, right. Oh, I should say this is one condition. Actually, what we are saying is the other way around. So, we say that this is actually less. Okay, so what we are saying is the other way around. Now, you will have both, not only this df has become more than 3/7 of your XU. Then you will have both, because now for here you see here, this is the truncated area that we have to do. So, this has both constant region plus some truncated parabolic region, right. So, both of them. For that, the code is saying that you can, the equivalent depth of the flange df, instead of df in your calculation you can take yf as 0.156 XU plus 0.65 df. It is an approximation. So, people have done a lot of strain compatibility approach on this, and they are finding that this is good enough. It gives you a very close calculations for that. Okay. So, the equivalent depth YF is substituted for DF in your expression for your moment resistance. Okay, that is what we have. So, you can get your values, right. Okay. So, this is for again using IS code approximate method for calculating flange sections. Instead of iterating in XU, now we are iterating in terms of stress that we are assuming, right. So, otherwise everything is same. Okay.